Okay, so let's continue from here. Any questions about what we've done so far? Okay, so we were up to these relationships that I cross J is equal to K and so on. And so we're going to do this problem. So they want us to figure out, to compute this over here. So I'm just going to look at what they did. So first you multiply, you factor it. FOIL. So 2i times 3j, 2i cross 3j, and so on. And then the 2 times 3 becomes 6, I cross j becomes I cross j plus, and then 2 times 5 is 10, I cross k, and so on. And so then you get 6k minus 10j minus 3i. And so it's fairly straightforward. The next problem over here in example 5 is a physics problem. And I don't want to focus on this problem, but this problem, example 6, is a torque problem, and I do want to go over it. So like I said before, the torque is going to be equal to R cross F, where F is the force. So for example, if you have a wrench over here, then F over here is the force that you apply to a certain point, and R is the distance from where the wrench is going around to where the force is being applied. And so then if you take the cross product, you're going to get the torque. And you will notice that in these type of pictures, the torque is going to be in the z direction. So it's going to be coming out of the plane, something like that. And so for their specific example, they want us to find the torque for the following two examples. So the first example is for the force being this and for R1 being that. So let's do that. So the torque is equal to, so torque 1 is equal to R1 cross F1, which is going to be equal. And so then we're going to have the vector R1, which is 0.5, 0, 0, cross, and then the F1 vector is going to be the vector 0, 60, 0. Now, because these vectors are fairly simple, we can just rewrite this as 0.5i cross 60j, which is going to be equal to 0.5 times 60 I cross j, which is going to be equal to k. So like I said, the k is in the z direction. So you can imagine if we redraw this picture and we put the wrench over here. So here's my x, my y, and my z. So you put the wrench over here. So here's your wrench. And then the force over here is going to be going in that direction. So this is your F1. And then this over here is your R1. It's the distance from here to there. And then the torque is going to be in the k direction or in the z direction. So it's something like this. And this is your torque. Okay. And so then for the second problem, or sorry, for the second part of the problem, so we're going to have that T2 is going to be equal to R2 cross F2, which is going to be equal to, so it's going to be equal to 50, negative 50, 0. Oh, sorry, this is F2. R2, which is 0.3. Okay, so let's do 0.300 cross this. Okay, so now this is equal to, and we can do this with the cross product, or we can use the rules that we just learned. So this is 0.3i, and we only can do this because of that there's only one component in the R1, sorry, in the R2, this 0.3. Everything else is 0. That's why it's fairly easy to do the cross product here, and we don't have to look at the formulas that we had before. Okay, so now this times this is going to be 0 because I cross I is 0. So this is going to be equal to negative 0.350, and then I cross j is k. And that's how we do the second problem. Any questions about this? Is it clear? Okay, can you hear me?
Yeah, sounds good.
Okay, so now there are 3 areas that they want us to be able to find using the cross product. And the first one is this area. So if you have a V and a W, then we can create a parallelogram by putting the V up here and putting this W over here. So now this is a parallelogram, and we would like to be able to find its area. Now the V and W can be in R3, so the parallelogram is just moving the V over here and imagine that we're looking at this flat portion and we just want to find that area. But the question is, how can we find this area? So like I said before, the 2 very important equations for dot product and cross products are, so for the dot product, it's V dot W is equal to the magnitude of V times the magnitude of W times cosine of the angle between V and W. And for the cross product, it's the magnitude of V cross W is equal to the magnitude of V times the magnitude of W times sine of the angle between them. So in order to find the area of this parallelogram, what we need, well, the area, so let's call it A1, is equal to the base, which is the magnitude of V. So first it's equal to the base times the height, and that's going to be the magnitude of V times the height. Now, what is the height over here? So the height, this is the height, and this over here is my angle. In order to find this height, I can also look at the magnitude. So H is equal to the magnitude of W times cosine, times sine of theta. Because this W, if I take the magnitude, it's like I'm looking at R over here, and then I project it into the Y direction, right? And we know that Y is equal to R sine of theta. So in order to find my Y, which is also my height, I need to look at this equation. So that's my height. So then this thing is going to be equal to the magnitude of V times the magnitude of W times sine of theta. Now, the area is positive. So generally in this case, when the sine, we would take the absolute value of the sine. So yeah. Now, this over here is going to be equal to the absolute value. So this over here is equal to the magnitude of V cross W. Oh, sorry, we don't even need an absolute value over here. Okay. So this is going to be equal to the magnitude of V cross W. And that's the area of a parallelogram. And then the second area that they might want you to find, and again, there are only 3 different areas that we're going to focus on for cross products. And because we're not doing integration, I think that that would basically be it. So yeah, there are 3 areas that they would like you to know. So again, the first one is how to find the parallelogram, and that's just by taking the cross product of your vectors and finding the magnitude. And then the second area that they would like you to find, so that's going to be the triangle. So now if you have over here V and you have W, you can look at this triangle and they would like you to find this area. So it's going to be 1/2. So this triangle can be extended to a parallelogram where that's V again, and this is W again. So this is going to be equal 1/2 of the thing above, which is the absolute value of V cross W. So these are the two areas that they would like you to know. And then there's going to be a volume, which we're going to get to in a second. So going back here, the area of a parallelogram is going to be the magnitude of V cross W. And here is your V cross W, and it's going to be the magnitude, and that's going to get you the area of this parallelogram created by V and W. And the area of the triangle created by V and W is 1/2 of that. Any questions? Okay, so here are the two equations, area of the parallelogram, V cross W, magnitude, and the area of the triangle is 1/2 of that. And like I said, the proof for this, oh, sorry, do they probably talk about the proof above. Okay, now the next thing we would like to be able to do is find the area of a parallel pipette. So if you have three vectors, vector V, the vector W, and then the vector U. And now this creates a parallelepiped. So here we can create a parallelogram down here. And then on top, we just extend it. And here's our parallelepiped. And we would like to find the volume of this thing. So let's call it V3, the volume of our parallelepiped. And so we can first say that this thing is equal again to base times the height of this parallelepiped, where the base over here is this thing down here. And the height we'll get to in a moment. But first, in order to find the base, well, the base is the area of this parallelogram. So it's going to be equal to the magnitude of V cross W. So that's going to be our base. Now, our height, well, we can imagine first that we find the cross product. So let's first imagine that this vector over here is the vector V cross W. So it's normal. It's a vector orthogonal to both V and W. It's pointing out, and it's normal to this parallelogram. And so what we can do is we can try to project this U onto V cross W. So we can find the projection over here of this vector. We can find this projection, and that's going to be the height of our parallelogram. So how can we do that? So here's our angle, and we can say that that our height is going to be equal to our V cross W dotted with U over the magnitude of V cross W. So this is just a projection of U onto V cross W. So now when we look at this equation, this is going to be equal to V cross W times V cross W dotted with u over the magnitude of v cross w. And now these are going to cancel. And this is going to get you, and I'm just going to put the u on the other side because that's how they write it, u dotted with v cross w. And we take the absolute value of this just because of the area is positive. And this is going to be our area. Any questions about this? Okay, so like I just mentioned, so the base over here of this, the base is the parallelogram for this parallelepiped, and it's created by V and W. And so the area of the base is V cross W. And the height of this is going to be U dotted with cosine of the angle, which we can figure out the height either by looking at the projection or by just using cosine, because that we can take our U, the magnitude of U over here, and we are projecting it over here, which is the same as looking at cosine of the magnitude of u. That would give us our height. So this is our height. And okay, so then this over here, this is the dot product of v cross w and u. And so then we get that the volume of our parallelepiped is going to be u dotted with v cross w. So now they call this, and I generally, you don't see that this often in multivariable calculus. Like this doesn't appear that much other than in the case of a parallelepiped, but we call this the scalar triple product. And we can also use the determinant to find the scalar triple product. And the reason is, if you have, this is your u, this is your v, and this is your w, then u dotted with v cross w, well, that's the same as u. And then v cross w, well, that's just opening it up using the cross product, the formula for the cross product, which is equal, so this u has a u1, it's u1, u2, u3. So when we dot it, we get u1 times this minus u2 times this plus u3 times that. And that's the same as looking at this, u1, and then we're left with this matrix, v2, v3, w2, w3, minus u2, and then we're left with this matrix, v1, v3, w1, w3, and then lastly v3, and then we're left with the matrix v1, v2, w1, and w2, which is the determinant of u, v, and w. So that's another thing that you can do. If you have the vectors u is equal to u1, u2, and u3, v is equal to v1, v2, and v3, and w is equal to w1, w2, and w3, then the area of the parallelogram spanned by these, or created by these three vectors, so v3, is going to be the determinant of u1, u2, u3, v1, v2, v3, w1, w2, w3, which, like we said, is equal to the magnitude of u dotted with v cross w. Any questions about this? Is it clear?
Yes, it is.
What was that? Sorry.
Sorry, yes, it is clear.
All right, thanks. Okay, so now they give us this theorem, which says what we just looked at, that the volume is equal to u dotted with v cross w, which is the same as the determinant. So they want us to do the following example. Let v equal to this vector, W equal to that vector. So first they want us to calculate the area of the parallelogram spanned by these two things. So let's just do that. So for A, we're going to have that the area of this parallelogram, so A1, is going to be equal to the magnitude of V cross W. So now V cross W, so now this is going to be equal to I, J, K, and then 1, 4, 5, -2, -1, and 2. And then this is going to be equal to I times 8, and then this minus minus becomes plus, so plus 15, minus j times 2, and then this minus cancels with that minus, so minus 10, but then plus 10, and then plus k times, this is 1, and this minus cancels, so you get 7. Okay. So now the next part, so now we have the vector. Sorry, this is 5. So now we have the vector 13, -12, and 7. So the magnitude of this vector is equal to the square root of 13 squared plus -12 squared plus 7 squared. And that's going to be our magnitude. And they tell us that it's approximately 19. So that's going to be the area of our parallelogram. Any questions about this? Okay, so now for the next question, they ask us to find the volume of the parallelepiped in figure 12. So if you look at figure 12, here's the V and the W that we just looked at. And so this over here is the parallelogram that we were just looking at. And then what happens is the U, we can think about a new vector over here, which is the vector U. And U is going to be the vector 0, 0, 6, right? Because that over there was a 6. I apologize. Yeah, that is 6. So it's going to be 0, 0, 6. And we know that the area of this parallelepiped is going to be equal to, so the area, the volume is going to be equal to U dotted with the absolute value of U dotted with V cross W. And we already know what V cross W is. So let's go back down here. So U dotted with V cross W is going to be equal to 0, 0, 6 dotted with 13, -12, and 7. So this times that is 0, plus this times that is 0. So this is going to be equal to 6 times 7, which, yeah, is 42. So that's that. Any questions? Okay. So now, if we're in R2, so let's say we're in R2, and we have two vectors. So here's my X and here's my Y. And we have two vectors. Let's say this is the vector V, and this over here is the vector W. Now this V is equal to V1, V2, and this W is equal to W1 and W2. So if I ask you to find the area of the parallelogram created by these two vectors, and you try to use the formula we've been using until now, well, then you might say, okay, so the area is equal to the magnitude of V cross W, but then this is going to be equal to this of I, J, K, and then over here we only have two components, like V1 and V2, so what goes here? And over here, same thing, W1, W2, so what goes here? And the answer is, well, we can imagine that we are really in 3 dimensions, so we can add a Z over here, and then we can add a component over here, but it's going to be 0, and another component over here that's going to be 0, which means that over here what we're supposed to be putting is 0 and 0. And now if we take this determinant, we get, or this cross product, we are going to get this I times, and then the determinant. So this V2 times 0 is 0, and this W2 times 0 is 0, so it's I times 0, minus J, and then over here we're going to have V1 times 0 is 0, minus W1 times 0 is 0, so J times 0 again, plus K times, and then we're going to have V1 times W2 minus W2 times V1, so this is going to be K times V1 times W2 minus W2 times V1. Now, if you notice, this over here is the same, so this is equal. And if you take the magnitude of this, so first we're looking at the magnitude of this cross product. So here, that's the magnitude. And over here, we're also kind of looking at the magnitude of this cross product. So I'm going to do that over there. Okay. So now the magnitude of this thing is going to be equal to V1 W2 minus W2 V1, right? And we square this and we take the square root, so we're left with this. So that's going to be our area. And notice that this is the same as the determinant of V1 W2 W2 V1. So if we're in 2 dimensions and we have, this is equal to the determinant of V1 V2 W1 W2. V1 times W2 minus W minus
W1 V2.
Yeah, correct. Okay, minus W1 V2. Yeah, minus W1 V2. So yeah. Okay, perfect. So now this is the determinant, yeah? 1 second. So this over here is 1 second, W1 V2. Okay, perfect. Okay. So like we said, again, if you have the area in 2 dimensions, then we can extend, we can add a 0 and a 0. This over here is 0, that is 0, and then this over here, we are just left with that. And so the area is the absolute value of this determinant, which is so on and so forth, which is going to be equal to the absolute value V1 W2 minus W2 V2 W1, which is the determinant of this. Okay. So now they want us to compute the area of the parallelogram in figure 14. So here we are. And we have 2 vectors in R2. So we are going to say that the area is going to be equal to the absolute value of the determinant of V1, V2, W1, W2, which is going to be equal to the absolute value of, okay, determinant of 1, 4, 3, 2, which is going to be equal to the absolute value of 1 times 2, which is 2, minus 3 times 4, which is 12, which is going to be equal to 10. Any questions about this? Okay, so the next part over here, they prove what we proved about the triple cross product, and then they prove the relationship. They prove this relationship that the magnitude of V cross W is equal to the magnitude of V cross the magnitude of W times sine of theta. I'm not going to go over the proof. It uses, this is the fact that we can use cosine over here is and the dot product over here. So if you take this and you get this minus this over here, then this is going to be what we had minus this with cosine over here. That's what the dot product gives us. And then we can switch from cosine to sine the way we know how to do. And that's how we get from this to sine. So we basically use the formula V dotted with W is equal to the magnitude of V times the magnitude of W times cosine of theta to get this. And we proved this over here, if you remember, from the law of cosines. So, oh yeah. Any questions about this? Okay, so let's go over the summary. Oh, sorry. So like we said, the determinant of a 2 by 2 matrix is given like that. The determinant of a 3 by 3 matrix is given like that. And the cross product is given like that, where you put an I, J, and K over there. Then V cross W is orthogonal to V and W. Like we saw, we look at the dot product of V dotted with V cross W, and we got that this is equal to 0. The most important formula from this section, I think, is this. That V cross W, the magnitude is the magnitude of V times the magnitude of W times sine of theta. And like we said, the cross product represents sine with vectors, and the dot product represents cosine. Okay, and then we saw this formula is fairly straightforward. If you flip them, the vector goes in the opposite direction. So you get a negative. And these relationships, we said, were fairly obvious. And then we used the fact that the cross product and sine are very similar to show that the area of the parallelogram spanned by V and W has this area. And then we use that fact to show that the triangle spanned by V and W has this area, just divide by 2. And then in order to prove the relationship, in order to prove this relationship, we just showed what the determinant was, and we showed what this was, and they ended up being the same. And we had that the parallelogram spanned by U, V, and W is equal to this. And this kind of comes out from the fact that the dot product is being used to find the height of our parallelepiped, and the cross product is being used over here to find the area of the base of our parallelepiped. Any questions about this? Okay, so let me see what the next section is, but I do believe we should probably stop here. Just 1 second.
I have a question.
Yeah.
So, do we have to do the learning things that are on the website for the homework, or are you still only posting homeworks and we're not supposed to do this?
Yeah, no, so I think I confused a couple of people with some emails. It doesn't look like I'm not posting homework. I'm not posting the specific learning curves or the homework. I just put in the due date. So I was told in the beginning that there will be homework and learning curves, but it doesn't look like the person in charge of posting the homeworks is doing that. So for now, yeah, please do the learning curves, and that will count for as the homework. And hopefully we'll figure the other part out soon. Yeah, okay.
Thank you.
Any other questions?
So we're gonna have a quiz this week. Where would that be?
So I'm going to post it on Canvas, and it will be on Friday, and you'll have a certain amount of time from when you start to hand in the quiz. It'll be something like you have to scan in the pages that you work on and post them on Canvas.
Okay, thank you.
That'll be by Friday. Okay, so I don't want to start this new topic right now, so I think it's better if we just end early. Are there any other questions or?
Professor, what material will the quiz cover?
Dot products and cross products. Okay, so basically everything that we did until here with regard to dot products and cross products. So
do you know when the quiz will be accessible for us to take on Friday? Like what time?
Like Friday morning, it should be accessible, and it will be accessible basically the whole day. And but once you start it, you will only have a certain amount of time to finish and post it.
Perfect, thank you.
Okay. Yeah, so the quiz can have questions like, oh, find the area of this triangle, or find the projection of one vector onto another, or find the distance between 2 points. So basically questions like that, fairly straightforward and pretty similar to the learning curve problems. Okay? Any other questions?
Are there any other problems besides the learning curve problems that we should look at for the quiz?
No. Just learning curve problems. Those type of problems are the ones that will appear for now. Again, I'm going to try to get the homeworks up, but for now, they're not being posted. So yeah, just like problems very similar to the learning curve problems. That's basically what will appear.
Thank you.
Any other questions? Okay. Have a nice day, and I'll see you next time.